Entering the exciting world of PyTorch. Welcome to artificial intelligence. This journey starts with PyTorch, a powerful tool for building intelligent systems. PyTorch is a deep learning framework developed by Facebook's AI research lab. It's become a favorite among researchers and developers for its flexibility and efficiency. This tutorial is your guide to mastering PyTorch. Get ready to dive in and unlock the potential of AI with PyTorch. Why choose PyTorch stands out in the crowded field of deep learning frameworks. Its dynamic computational graph allows for flexible and intuitive model building. Modify your neural network on the fly, making experimentation smoother. PyTorch is known for its speed and efficiency. It leverages GPUs to accelerate computations. PyTorch boasts a vibrant and active community. This translates into a wealth of resources and tutorials. Practical applications of PyTorch. PyTorch's versatility spans various industries. It powers image classification, object detection, and segmentation, used in self-driving cars, medical imaging, and quality control. In NLP, it fuels sentiment analysis, translation, and chatbots. PyTorch's impact extends beyond these domains. Preparing your workspace. Before we embark on our PyTorch journey, it's essential to set up a dedicated workspace on your computer. This workspace will house our PyTorch installation, project files, and dependencies. Choose a location and create a folder named PyTorch Projects or similar. Ensure you have permissions to modify files. Once ready, proceed to install PyTorch. Section 2. Installing PyTorch. Let's install PyTorch, the heart of our AI endeavors. PyTorch offers various installation options for different operating systems. The easiest way to install PyTorch is using pip. Open your command prompt and type the following command. This command instructs pip to download and install PyTorch. Once complete, verify it by typing "If no errors, congratulations, you've successfully installed PyTorch." Section 3. Creating a virtual environment. Create a virtual environment for clean and isolated PyTorch projects. It helps manage dependencies and prevent conflicts. Navigate to your PyTorch workspace and execute the command. This creates a new virtual environment named PyTorch_NV. To activate, type the command for your OS. Your prompt now shows the virtual environment name. Install packages with pip to keep projects organized. This ensures project stability and reproducibility. The building blocks of data. Understanding tensors. The building blocks of data. In PyTorch, tensors are the fundamental building blocks of data. Imagine tensors as multi-dimensional arrays holding numerical data. They are the containers that carry information for AI models. We can create tensors of various dimensions to represent different data types. Understanding tensors unlocks the power of PyTorch. They are the language for communicating with AI models. Section 2. Creating and manipulating tensors in PyTorch. PyTorch makes working with tensors a breeze. Let's start by creating a simple tensor. Open your Python environment and type import torch x =torch.tensor 1, 2, 3, 4, print x. This code snippet imports PyTorch, creates a tensor x with values 1 to 4 and prints it. PyTorch's tensor powers don't stop there. We can perform various operations on these tensors. Create tensors y and z by adding and multiplying x by 2. Operations are element-wise, modifying each element individually. PyTorch offers functions to reshape, combine, and transform tensors. A simple example. Section 3. Tensors in action. A simple example. Let's solidify our understanding of tensors with a practical example. Suppose we want to represent the heights of students in a class using a tensor. We've created a one-dimensional tensor named heights to store this data. We divide the heights tensor by 100 to obtain the heights in meters. This example shows how tensors efficiently represent and manipulate data in PyTorch. Unleashing the power of tensor operations. Tensors are the raw materials, and tensor operations sculpt them into intelligent models. PyTorch provides operations to manipulate tensors for complex computations. We've explored basic arithmetic operations like addition and multiplication. From element-wise operations to matrix manipulations, we'll explore deep learning algorithms, PyTorch's well-designed API and clear documentation make it easy to grasp these concepts. Buckle up as we transform raw data into meaningful insights. The Heart of Deep Learning. Section 2, Matrix Operations, the Heart of Deep Learning. At the heart of many deep learning algorithms lies the power of matrix operations. From image recognition to natural language processing, matrices efficiently represent and manipulate data. PyTorch excels with functions for matrix multiplications, transpositions, and more. Matrix multiplication connects layers of neurons in neural networks. PyTorch's function handles two-dimensional matrices and higher-order tensors. PyTorch also transposes matrices, extracts diagonals, and calculates determinants. Essential for dimensionality reduction, feature extraction, and solving linear equations. Mastering matrix operations in PyTorch is crucial for deep learning models. These operations form the backbone of intelligent systems. Section 3, Reshaping Tensors, Adapting to Different Data Structures. Data in the real world comes in various shapes and sizes. One moment, we might be dealing with a list of numbers, and the next, we might encounter a table with rows and columns or even a multi-dimensional image. PyTorch's tensor reshaping operations provide the flexibility to adapt our data representations. The ViewView function is our go-to tool for reshaping tensors. It allows us to change the dimensions of a tensor while preserving its underlying data. For example, we can transform a one-dimensional tensor into a two-dimensional matrix. PyTorch offers functions like reshape, transpose, and permute. These functions are invaluable for convolutional and recurrent neural networks. Mastering tensor reshaping ensures seamless integration and optimal performance. Section 4, Broadcasting, Expanding the Horizons of Tensor Operations. Imagine trying to add a single number to every element in a list. You could loop through the list and perform the addition element by element. But what if you had a multi-dimensional array? This is where PyTorch's broadcasting mechanism steps in. Broadcasting allows operations on tensors of different shapes if their dimensions are compatible. PyTorch expands the smaller tensor to match the larger tensor, making our code concise and efficient. Broadcasting simplifies tensor operations, especially in neural networks. It lets us focus on high-level logic without low-level details. Section 1, Accessing Tensor Elements, a precise approach. Imagine having a treasure chest filled with valuable gems. That's akin to what we do with tensor indexing. We use indices to access elements in a tensor. Tensors can have multiple dimensions, so we need a set of indices. In PyTorch, indexing starts at 0. We use square brackets after the tensor's name. For example, would give us the value 1. Section 2, Slicing and Dicing, Extracting Subsets of Data. Imagine extracting a handful of gems from our treasure chest. Slicing lets us select a range of elements, creating a smaller subset. In PyTorch, we use the colon within square brackets to define slices. Slicing is powerful with multidimensional tensors, extracting rows, columns, or sub-blocks. This is invaluable in data pre-processing, feature engineering, and model training. Unlocking Flexibility, Section 3, Advanced Indexing Techniques. Unlocking flexibility, PyTorch offers advanced indexing methods for greater flexibility in accessing and manipulating data. Boolean indexing allows us to select elements based on a condition, provide a tensor of Boolean values, and PyTorch selects elements corresponding to true values, integer array. Indexing lets us select elements using a list or array of indices, useful for accessing elements non-contiguously or rearranging them based on a specific order. Section 4, Indexing and Slicing in Practice. Let's tie everything together with a practical example. Suppose we have a tensor representing a batch of images. We can use indexing and slicing to extract specific regions of interest. For instance, we could crop all images to a specific size or extract a particular channel. Combining these techniques allows complex data manipulations, preparing our data for training or analysis. Section 1, The Magic of Broadcasting. Imagine you're preparing a batch of cookies and you want to add a pinch of sugar to each cookie dough ball. You wouldn't sprinkle sugar individually on each ball, would you? Instead, you'd likely sprinkle it evenly across the entire batch. Tensor broadcasting in PyTorch is similar to this efficient sprinkling process. It allows operations on tensors of different shapes as long as their dimensions are compatible. PyTorch handles shape mismatch, making our code concise and efficient. This magic simplifies many common operations in deep learning. Section 2. Rules of engagement when broadcasting works. Broadcasting offers great flexibility, but not all shape combinations are compatible. PyTorch follows rules to determine if tensors can be broadcasted. Dimensions must be compatible. They are compatible if equal or 1 is 1. PyTorch compares dimensions from right to left. If compatible, the smaller tensor expands to match the larger. If not, PyTorch raises a broadcasting error. Section 3. Broadcasting in action, practical applications. Let's solidify our understanding of broadcasting with a few practical examples. Imagine we have a tensor representing a batch of images. We want to normalize each image by subtracting the mean pixel value. Using broadcasting, we can achieve this efficiently. First, we calculate the mean pixel value across the batch. Then, we subtract this mean tensor from the original image tensor. Broadcasting ensures efficient subtraction without explicit looping. Another application is element-wise operations between a tensor and a vector. Suppose we have a data set of student grades stored in a matrix. We can scale each student's grades by multiplying with a vector of scaling factors. Broadcasting ensures each student's grades are scaled by the corresponding factor. Section 4. Broadcasting, a performance booster. Broadcasting offers significant performance benefits. PyTorch broadcasts a tensor without creating a data copy. It performs operations as if expanded, without memory overhead. This makes broadcasting faster than explicit looping, especially with large tensors. In deep learning, broadcasting optimizes models and reduces training times. Understanding and applying broadcasting principles harnesses PyTorch's full power. Embracing the power of automatic differentiation. Imagine solving a complex puzzle by hand, meticulously trying different pieces and backtracking. Now, imagine a magical tool that instantly tells you how to solve the puzzle efficiently. That's automatic differentiation, and PyTorch's AutoGrad module is our magic wand in deep learning. It automatically calculates gradients crucial for neural networks. Gradients guide us in adjusting model parameters to minimize errors. With AutoGrad, PyTorch handles the heavy lifting, letting us focus on model design and training. Section 2. Under the hood, how AutoGrad tracks gradients. To appreciate AutoGrad, let's peek under the hood. At its heart is a computational graph showing data flow through operations. Each node represents an operation, and edges show data flow. For gradients, AutoGrad traverses this graph in reverse using the chain rule. It handles gradient formulas automatically, easing our work. Section 3. Harnessing AutoGrad for deep learning. Let's bring AutoGrad to life with a concrete example. Suppose we're building a simple neural network to predict house prices. Our network takes features like square footage and outputs a predicted price. During training, we compare its predictions to the actual prices. The difference is our loss. Our goal is to minimize this loss. Here's where AutoGrad steps in. We tell PyTorch to track gradients. After calculating the loss, we call. This triggers back propagation. AutoGrad calculates gradients for each parameter. These gradients guide us to reduce the loss. Section 4. Beyond the basics, advanced AutoGrad techniques. PyTorch provides tools for fine-grained control over gradient calculations, disabling gradient tracking. Temporarily disable gradient tracking for specific operations. Useful for computations without affecting gradients, like model evaluation. Gradient clipping prevents gradient explosion by scaling down gradients. Custom gradient function. Define custom gradients for unique operations. Mastering these techniques allows fine-tuning models for optimal performance. AutoGrad's flexibility solidifies PyTorch's role in AI research. The structure of a neural network. Section 1. Laying the foundation. Imagine a team of experts working together to solve a complex problem. This is analogous to how a neural network operates. A neural network consists of layers of interconnected nodes or neurons. The input layer receives raw data, and the output layer produces predictions. Hidden layers learn complex data representations. Connections between neurons have weights adjusted during training. The architecture includes layers, neurons, and their connections. PyTorch's NN module, your neural network toolkit. Building neural networks from scratch can be daunting, but PyTorch's NNE module simplifies the process. It provides high-level abstractions for defining and working with neural network components. Think of it as a toolbox filled with pre-built Lego blocks for different parts of a neural network. We have blocks for linear layers, convolutional layers, activation functions, and more. Our job is to assemble these blocks to create our desired network. We define our network by creating a Python class that inherits from NNR module. This class acts as a blueprint, specifying the network structure and data flow. We also define a forward method to outline the sequence of operations on the input data. Section 3. A simple network classifying handwritten digits. Let's build a simple neural network to classify handwritten digits. We'll use the MNIST dataset, a classic benchmark in machine learning. Our network will have 784 input neurons, one for each pixel, 128 hidden neurons fully connected, output layer, 10 neurons, one for each digit. We'll use the ReLU activation function. This network shows the basics of a PyTorch neural network. Section 4, from linearity to non-linearity, activation functions. The real world is rarely linear. Relationships between variables are often complex and non-linear. Activation functions are like spices in a recipe. They add flavor and depth to our models. They introduce non-linear transformations, allowing our networks to learn complex functions. Without them, neural networks would be limited to linear regression models. Activation functions break this linearity, capturing intricate patterns in data. Common activation functions include sigmoid, ReLU, and TARN. Choosing the right activation function depends on the problem and architecture. How neural networks adapt. Imagine teaching a child to ride a bicycle. They might wobble, fall, and need guidance. Neural networks go through a similar process during training. At the start, weights and biases are initialized randomly. It makes predictions, compares them to actual values, and adjusts parameters. With each iteration, it gets better at understanding data patterns. Each adjustment brings it closer to being a powerful, predictive model. Loss functions, guiding the network towards accuracy. Loss functions measure network performance. They guide the network to minimize errors. For classification, cross-entropy loss is preferred. Section 3 optimizes fine-tuning the path to convergence. Optimizers guide us to minimize the loss function. They ensure efficient convergence. ADAM and RMSprop adapt learning rates for faster convergence. The training loop. The network iteratively learns from the data. Forward pass, loss calculation, backward pass, and parameter update. Repeat for multiple epochs. Monitor loss to track progress. A steady loss decrease indicates effective learning. Section 1. Assessing model performance. We evaluate our model with unseen data. This process is called model evaluation. Overfitting occurs when a model fails on new data. We use a validation set to understand the model. Section 2. Metrics that matter, quantifying success in AI. We need quantifiable metrics to capture our model's performance. Common metrics include accuracy, precision, recall, and F1 score. These metrics provide a standardized way to compare models. This enables informed decisions about deployment and development. Preserving your AI's knowledge. Section 3. Saving and loading models. PyTorch provides a mechanism for saving and loading models. Save the entire model or just the weights. Use torch save to save. Use torch load to load. Reuse models, resume training and experiment. Essential for efficient AI development. Evaluating the bigger picture. Beyond accuracy, consider interpretability, fairness, and robustness for responsible AI. Transfer learning leveraging pre-trained models. Transfer learning leverages pre-trained models to accelerate AI endeavors. Pre-trained models understand general features from vast datasets. Achieve state-of-the-art results with less training data. Transfer learning is efficient for various AI tasks. Adapting models to new domains. Fine-tuning involves adjusting pre-trained models to fit our target dataset. PyTorch offers techniques like feature extraction and layer-specific fine-tuning. Strategy choice depends on dataset and task complexity. Section 3, GPU acceleration, unleashing the power of parallel processing. GPUs perform computations on multiple data points simultaneously. PyTorch integrates with GPUs with minimal code changes, crucial for large-scale deep learning problems. Section 4, Beyond the Horizon, exploring the frontiers of PyTorch. PyTorch leads deep learning evolution. Key areas: PyTorch Lightning, quantization, federated learning. PyTorch offers tools and flexibility for AI. PyTorch is our companion in AI's future. Embracing the future of AI with PyTorch. You now possess the knowledge to embark on your own AI adventures. Mastering PyTorch requires practice, experimentation, and a thirst for knowledge. Embrace the iterative nature of deep learning. Experiment with hyperparameters and explore the PyTorch ecosystem. The future of AI is shaped by those who explore and experiment. With PyTorch, you can build intelligent systems that shape a better tomorrow. Section 2, Continuing the Journey, resources for further exploration. Your journey into the world of AI doesn't end here. The PyTorch community is vibrant and supportive. Explore the official PyTorch documentation, join online forums, and participate in workshops. The most effective learning comes from hands-on experience. Seek out projects that ignite your passion. With PyTorch, transform your AI aspirations into reality. Congratulations on completing our comprehensive PyTorch tutorial. You have successfully mastered the basics as well as some advanced techniques. Now it's time to elevate your expertise further. Ready to take your skills to the next level? Join our comprehensive course, Foundations of Artificial Intelligence and Machine Learning, with more in-depth learning and hands-on projects. In this course, you will gain practical experience with advanced AI techniques and access to exclusive content. Click the next video or link below to learn more. Don't forget, like, share, and leave a comment. Thank you for watching.